Now, there are different formulations like which you can use to represent this filtering. And the basic one is called correlation. And the mathematical formulation for correlation is you have two different functions, f and h. And what you do is you perform like element-wise multiplication of these two functions over some neighborhood, like in this case, like k and l, if it's like two-dimensional function. And correlation is used to find out if two different functions are similar or not. And this you have seen in the first lecture when we're trying to perform object detection using pattern matching. If the patterns match, then we get like a very high response, which means the correlation is very high. So this is directly coming from statistics. Okay. In this case, what we do is if we have to use correlation to perform filtering, we represent the first function as image and the second function as kernel. So first function becomes something like this. The second function becomes this. So there's the image patch. This is your kernel. And the operation, if you go through like steps of this equation here, it's nothing but the steps I explained to you in the previous slide. You just perform element-wise multiplication and add those values up. All right. So that's correlation. The second way to represent filtering is convolution. And you might have heard of convolutional neural networks. We're going to study that in this course in very detail. Now, convolution, the mathematical formulation is almost same as correlation. We have two different functions, right? And again, we look into some neighborhood like of these functions. The only difference is we flip the second function. All right. So because we have these negative values in correlation, this was all positive. And again, it's the same representation, f is image, h is kernel. Now, if you have to represent convolution in form of correlation, what you can do is you take your kernel, because you have negative values, you can actually flip it in both the axes, x and y. So in this case, we are flipping like along x-axis. So this becomes positive. Then we can flip along y-axis. Then that will become positive, right? Then it's exactly same as correlation. So let's say this was the initial kernel. You flip along x, flip along y, you get this kernel. And then again, you can just perform correlation of this kernel with the image patch. It's the same equation. Okay. So you can see like correlation, convolution, exactly same thing. The only difference is the kernel values. Now convolution, like it's associative. These are some interesting properties. We can quickly go over these. So associative means like if you are performing convolution of G and I first, and then convolving that with F, it doesn't matter like what order you use. You can actually first convolve F and G, and then convolve the result with the second function. Okay, so it's associative. Now, just going over the definition. So convolution, it's like a filtering operation. So is like correlation. And so convolution is kind of giving you how much is the overlap between two different functions. All right. And we have the negative sign, which means that we actually shift the we shift the kernel over our function, and we try to find out like if there is some overlap or not. But the high level intuition remains the same, because correlation is also comparing two functions and finding out whether they are similar or not. Okay, so the basic idea remains the same. Now, before going to like the actual some of like, we'll go through some of the examples to perform filtering. There are like two other concepts which are very important. We'll see. So first is mean, and you all must know this already. Mean will be like you have different values, and you add those values and divide by the number of values, right? So it's the standard mean. And again, I could be just a number, it could be a matrix, it could be a vector, anything. Right? Now, an advanced form of mean is weighted mean, which I think is more relevant to us. And this weighted mean is also related to, we have been talking a lot about linear combination. Okay, so if you look at the numerator of this equation over here, this is a form of linear combination of all these values, right? And these W1, W2, all these are weights. The only difference is you normalize this value. Okay, so basically when we will perform filtering, we will see that most of the time it's going to be linear combination like this. And we are going to normalize with like the number of pixels we are actually operating on, the size of the neighborhood. So this is actually showing the filtering operation which we are going to use.